Right. Again, the constant function is f of x equal to b, and the domain is from negative infinity to positive infinity. Now, what is the range equal to? Anyone? What do you think?
B.
Just b, right? There's just one element there. So the range is going to be just b. So I use curly brackets because I just want to include one element in my range. So the next function is linear functions. I just want to give you one candidate here, just f of x equal to x. But linear function, we're going to focus on more in the next lecture when you talk about linear function, more specifically, equation of the line. We'll see. So the domain of this function is from negative infinity to positive infinity as well. The range is the same. It's going to be from negative infinity to positive infinity. The next function is square functions. We will then, or more, there's a general name for that, it's called the quadratic functions. We'll dedicate one lecture on quadratic functions. But for now, it's just going to use the example that f of x equal to x squared as the square functions. The domain in this case is from negative infinity to positive infinity, but the range is going to be different, depends on the functions that you have. So I'm just going to write the range for this particular function is from 0 to positive infinity. But again, you can have a different range, depends on different square functions. For example, if I move this down to -1, then the range will change from -1 to positive infinity instead of 0 to positive infinity. You with me on that? So the range is going to be slightly different, depends on the function. The domain is from negative infinity to positive infinity. The range in this case is from 0 to positive infinity. Again, I want to point out that you will have a different range, depends on different functions. For cubic functions, we're not going to spend a lot of time on cubic function, but the cubic function is the function with the power 3. Right? So the domain in this case is from negative infinity to positive infinity. And the range is the same from negative infinity to positive infinity. So for the next function is square root functions. You have an expressions under the square root as square root functions. For the domain in range, it depends on the functions that you may have a different domain range. But in general, to find the domain of the square root functions, what you do is you take the expressions under the square root and set that to be greater than or equal to 0. Right. So in this case, you only have x under the square root. So you take x and set that greater than or equal to 0. So that gives you the domain. Or you can write this from 0 to positive infinity. And the range is going to be different, depends on the functions that you get, but in this case, going to be from 0 to positive infinity. So for cube root functions or arc root function in general, we don't care much about the domain. The domain range is going to be from negative infinity to positive infinity. So it doesn't mean we don't really care. It just means that there's no formula for you to follow. But for square root function or even root functions, you need to follow a certain rule. That is the expression under the root, under the square root, under the fourth root, or in general under the even root has to be greater than or equal to 0. The next function is the reciprocal functions. Right. So for the reciprocal function, this is a fraction, as you can see. So the denominator has to be different from 0. So the domain is x different from 0. But in terms of the notations, interval notation, you can write this as from negative infinity to 0, union with 0 to positive infinity. For the range, again, depends on the functions. You can have a different range. In this particular case, the range is from negative infinity to 0, union with 0 to positive infinity. We will dedicate 2-3 lectures on something called rational functions. But we learned about rational expressions earlier. We took a test on that, but we're going to focus more on rational functions. There's a lot to learn about rational. All right, the next function is the square reciprocal function. So you have 1 over x squared. So again, you don't want the denominator to be equal to 0, so x is different from 0. But for the range, again, it depends on the function that you have. You may have different range. But in this case, the range is from 0 to positive, but do not exceed 0. So the line right here, going down, approaching the x-axis, the word is approaching. It's not going to touch or cross the x-axis. So therefore, 0 should not be included in the range. So the domain here is x different from 0, or the domain is from negative infinity to 0, union with 0 to positive infinity. And the range is from 0 to positive infinity. All right, the next function is absolute value function. So the graph looks like this, but the domain is from negative infinity to positive infinity. The range is from 0 to positive infinity. So this function is very nice and weird at the same time. So it's that please allow you to write piecewise defined functions that you learn a little bit later. But it's weird is that this has kind of like between here and it will define something called smoothness of the curve. The function is continuous, right? But you have kin, so it's not going to be something called differentiable. It's not smooth. That's differentiability concept, smoothness. So the domain in this case is negative infinity to positive infinity. The range is from 0 to infinity. So the concept of continuity and differentiability you will learn in calculus 1. You will see this function over and over again. We will spend a lot of time, maybe 2 weeks, on exponential functions and logarithmic functions and things related to exponential function and logarithmic functions. So exponential function it's going to be with this form, a to the x for a is greater than 1. Okay. There's another name for this. It's called the exponential growth functions. The domain in this case from 0 to positive infinity. Sorry, negative infinity to positive infinity. The range is from 0 to positive infinity. This graph is called exponential growth. The next graph is also an exponential function, but in the case where a is between 0 and 1. So this is called exponential decay. Eventually, everything will die out. So exponential function get used a lot in mathematics, physics, biology, and chemistry, especially in population dynamics. When you talk about the rate of change of population with respect to a certain area or certain time, the population increase exponentially, although it's not realistic, but it's a good model to study at the beginning of certain situations, especially when you look back at COVID-19, when it's first happening, a lot of papers or articles, they talk about the cases, infected cases increase exponentially. That they talk about exponential growth model. If there's not enough resources of food in general, the population can die down, eventually become distinct. Sorry. I'm learning here. Okay. So the domain in this case is from negative infinity to positive infinity. The range is from 0 to positive infinity, and this one is exponential decay. There will be other situations when you do graph transformations for exponential function, but these two graphs are more important. So the last graph I want to show here in the family of functions is the natural logarithmic functions. It's called ln of x, even though it's natural log, is ln. All right, so the domain here is from 0 to positive infinity, and the range is from negative to positive infinity. You will learn a concept called inverse functions later on in the course. A function can be an inverse of another function, and turn out that exponential function and logarithmic function are inverses of one function. So therefore, when you take a look at the domain and the range of these two functions, so let's take a look at this function right here. Sorry. This function right here and this function. All right. So the domain and the range gets what? The domain from negative infinity to positive infinity exponential function gets what to the range. And the range from 0 to positive infinity gets what to the right. So something like that is inverse of one another. All right. Any questions so far? Right. You will see this functions over and over again in this course in calculus sequences as well. Another type of functions I want to introduce to you is piecewise defined functions. If you go back to the lecture note that we have in the past, something like this in lecture 8, you have this type of function, this weird-shaped function. So this function is called a piecewise defined function because they combine by two many pieces. Okay. So piecewise defined functions. Give me 1 second here. So a function that is defined by different equations on different part of its domain is called a piecewise defined functions. All right, so example one, go back to the absolute value that we see earlier. So absolute value is actually a piecewise defined functions. So absolute value functions, f of x equal to absolute value of x is a piecewise defined functions. So here you have f of x equal to absolute value of x. There's two parts to this. The part that is positive x, if x is greater than or equal to 0. And is negative x if x is less than 0. And again, the graph of the absolute value of x look like this. All right. So for example, why do we study this type of graph function for that matter? It depends on the situation that we can tell a different story, give you a different story here. For example, if you have this absolute value of x, this type of graph, a piecewise defined function graph can tell a story about a car that's slowing down, if it's drive along this horizontal axis, it's slowing down, right? At some point, it's accelerating. Things like that. So this piecewise defined function is quite important in higher mathematics, even though it gets you a lot in everyday life situations. That, for example, when you record a video, let's say I'm recording my audio video here. When I record it, there's a lot of noise in the background. Now, how would you isolate those noises and remove that from the audio? What you're going to do is you run through something called the Fourier series, and so that's a big word. But anyway, they use the piecewise defined function in the background to isolate those noise and just pick up the noise that or the sound. Good. So there's a lot of use of that. A lot of applications to that piecewise defined function use in mathematics and physics. And for logarithmic functions, there's a lot of formula related to earthquake that measure each other. So a lot of fun stuff in mathematics, I suppose. I studied this, I teach this, so I have to say that now. All right, so the function, example 2. So the function f is defined with this formulation. So f of x is equal to 2x plus 3 if x is less than 0, and equal to negative 1/2 x plus 3 if x greater than or equal to 0. Now, it's a little bit different for piecewise defined function when you evaluate the output of the functions, right? Given some input. So in this case, they ask you to calculate f of -2, f of 0, and f of 2. And depends on the input, you may have to use a different output or different function. You with me on that? Okay. So for the first calculations, f of -2. So x is equal to -2. So the input is -2. Because x is equal to -2, you have to use the first function 2x plus 3 for the evaluations. You with me on that? Because the function is 2x plus 3 when x is less than 0. In this case, yes, x is -2, which is less than 0. All right. Now for f of 0, when x equal to 0, right here, x is greater than or equal to 0. When x is equal to 0, you have to use this function for the evaluations. So you need to use -1/2 x plus 3 for the second evaluations. And for the third evaluation, f of 2, x is equal to 2, which is greater than 0. Again, you use this function. You're okay with this? All right. So f of -2, right? So you u2 times -2 plus 3, which is -1. So you use the first function because x is equal to -2, which is less than 0 in this case. Now f of 0 is -1/2 times 0 plus 3, which is equal to 3. What time do we have to go? 110, 120? 120. Okay, thank you. Now for f of 2, you have -1/2 times 2 plus 3. So it is -1 plus 3. It's positive 2. Any questions on these evaluations? Good. All right, so let's graph this piecewise defined functions. Okay, so to graph it, it depends on the interval that you have. Right? So you have two different intervals here. X is less than 0 and x is greater than 0. So when x is less than 0, you work with 2x plus 3. And you just draw a table just like you did normally you want to draw something. And when you have x greater than or equal to 0, you use -1/2 x plus 3. Okay. All right. So I'm gonna make two different tables. Don't have to be a big table, just need 2 points for each table. So here is x, here is 2x plus 3. Remember, x in this case has to be less than 0. So I'm going to use x equal to -1, x equal to -2 for my input. So when x equal to -1, you have +1. When x equal to -2, you have -1. So you get 2 points, therefore you can draw this line. X equal to -1, +1 here. X equal to -2, -1 here. Anyone have a ruler? It's too big for my tablet. I'm gonna break it. You know, when I was in grade school back in Vietnam, the teacher used to use those two to hit on the. I'm not making this really happen. I do have TSD. All right, so you connect these 2 points together. So at x equal to 0. So bear with me here. Give me one more, 2 seconds, 2 seconds. All right, so you have x strictly less than 0. Okay, bear with me here. X strictly less than 0. So in that case, when you have something strictly less than or strictly greater than, you have an open circle. You okay with that? So that's how you graph it. So in this case, at x equal to 0, you have an open circle. Technology, right?
How would we graph it?
Closer. Eventually, this open circle will get cubed. This is just for this particular case. Sometimes that's sometimes create holes, just like what you saw earlier in lecture 9. So you have a closed circle here. That means x is greater than or equal to 0 here. This is open circle. Let's not get cubed. All right, now I need the second table for the second functions when x is greater than or equal to 0. So x here, you have negative 1/2 x plus 3. X is equal to 0, y is equal to 3, x is equal to 2, y is equal to 2. So that's 2. All right, so this line should be, let me change a little bit. Should be have 3 here. So open circle here. And this open circle get close by this. Okay. 0, 3, that 1 point, 2, 2, another point. All right, so that's the graph. This is the piecewise. Let's move on to the last example here. So you are given a piecewise defined function, you are given the graph, and you say, oh, what is the domain of this function? And you locate any intercepts. And the last part is to use the graph to find the range of the functions. All right. So this piecewise defined function is a little bit harder to draw out, especially with an x squared function. But there are 3 parts to the functions. The first part when x between -3 and 5. Right. So greater than x is greater than or equal to -3 and less than or equal to 1. Because of the equal sign you see in the inequality, you have a closed circle. Let's closed circle at 3, closed circle as this is sorry. This is wrong. Can you remove this equal sign? Sorry. That is wrong. So this should be removed. Just strictly less than 1. So x is greater than or equal to -3 and strictly less than 1. Because it is strictly less than 1, you have a open circle. Okay. All right. Now, the second part to the function is when x equal to 1, then you have the output to be equal to 2. Therefore, you have a closed circle. And for x strictly greater than 1, you have x squared, which is a parabola. Therefore, you have an open circle here. Good. All right. Now, what is the domain of the function? Like you saw something like this before. We did the test already. What is the domain? Okay, that's a good one. Okay, so from negative to 1, union with 1 to positive. Right. So that's good, right? I could give you full credit for that. But so -3, I assume that include -3 in this case because you start at -3. To 1, union with 1 to positive infinity. Do you include brackets here? Yes or no? Yes. No. Maybe. Which one? So you don't include the brackets, but what you include is you include an element of 1 here. Why is that the case? Because 1 is still defined, x equal to 1. You still have that in the domain. You with me on that? All right. So instead of breaking down into 3 different parts, you just combine everything together. All right. And to positive infinity. X. Do you see that? Everyone, do you see that? Do you understand why that is the case that we go from -3 to positive infinity? Even though, yes, we have 2 holes here at x equal to 1, x equal to 1 is still defined. The function is still defined as x equal to 1. So therefore, you still need to include that. So the domain in this case is from -3 to positive infinity. Do I have any x-intercept? What is x-intercept? 0.5, yes. So 1/2, 0. Y-intercept 0, 1, yes. Now, what is the range of the functions? -1, including? No. So start from -1, 2 to infinity. No. Even though, again, yes, you have a hole here, but this gets you. So from -1 to positive infinity.